30 times higher was the safe guess, but the real answer pushed past 40 against Earth's oceans. But that sounds too neat, and neat stories usually fall apart when you check how the number was actually built. Because if 3I/Atlas really carries water this extreme, the shock is not just the ratio, but the kind of world that had to make it. So what is the real reason 3I/Atlas has a water ratio unlike anything ever measured? At first, this looks like a simple headline about a strange comet from far away. Then you notice how many parts of the story do not fit the easy version. That is when the trail stops feeling finished and starts feeling alive. Subscribe if you want to stay with the people who follow the full trail, not just the loud first claim. Stories like this change when new measurements land, and the early watchers are the ones who see the real shape of it. Stay close, because the surface version of this story is not the true one. The object now called 3I/Atlas was first reported on July 1, 2025, by the Atlas Survey Telescope in Rio Hurtado, Chile. Later checks pushed its earlier sightings back to June 14th, which meant astronomers had a longer track of its motion than they first thought. That mattered right away because a longer track can tell you whether something is just visiting or whether it belongs here. And this one did not belong here. Its path was hyperbolic, which means it was not looping around the sun in a closed path like a normal comet or asteroid. Trace that path backward, and it clearly came from outside our solar system. That made it only the third known interstellar object ever found, after the first two visitors shocked astronomy in earlier years. So before anyone even looked at its chemistry, 3I/Atlas was already carrying a different kind of importance. But the path only told scientists where it was not from. It did not tell them what kind of place it came from. That answer had to come from the gas and dust pouring off the object as sunlight warmed it. And for this story, one chemical clue mattered more than all the rest. That clue was water, but not just ordinary water. Some water molecules contain deuterium, a heavier form of hydrogen with an extra neutron inside it. People sometimes call that semi-heavy water, and the amount of it compared with normal water can act like a frozen memory. It can tell you what the object's birth environment was like long before the object ever reached us. Here is the basic idea in simple words. When water forms in very cold places, deuterium can slip into molecules more easily than it does in warmer places. If that water stays cold and does not get cooked, blasted, or heavily changed later, the high deuterium signal can survive. So the water ratio is not just a number about chemistry, it is a weather report from the object's birthplace. That is why scientists care about something called the D to H ratio. D means deuterium and H means ordinary hydrogen. On Earth, in our oceans, that ratio sits at a known level, and comets in our own solar system usually stay in a certain range around it. If a new object lands far outside that range, it is like finding a passport stamped by conditions we do not usually see. Now this is where the trail starts to twist. The most important measurement came from ALMA in Chile, the Atacama Large Millimeter and Submillimeter Array. That set of radio telescopes could look at 3I/Atlas only in a narrow window, just 6 days after it passed closest to the sun. Most telescopes cannot safely point that close toward the sun, so the chance was brief and rare. Luis E. Salazar Manzano, a PhD student at the University of Michigan, led the study with Teresa Paneque Carreño and a wider team. They were not just taking pretty pictures. They were trying to catch specific signals from molecules in the cloud around the comet, called the coma. If they could read those signals well enough, they could test whether this visitor was merely strange or truly extreme. And then one detail made the whole problem harder. ALMA clearly detected HDO, the form of water that includes deuterium. But ordinary water, H2O, fell below the detection limit in those observations. So the team had part of the answer in hand, while the other part had to be inferred from a model using methanol lines, which are signals from another molecule. That is exactly the kind of detail that makes a careful person slow down. If normal water was not directly seen in the same way, was the big headline number too bold? Was this a real chemical shock, or a chain of smart guesses stacked on top of one another? Those doubts were reasonable, and they had to be faced before any grand claim could survive. So before I show you the number that changed the story, make your call now. Do you think the team had found a true sign of an alien birthplace, or a tricky result built from limited data? Drop your best prediction in the comments before the next step lands. The number survived. In the study accepted by Nature Astronomy, the team reported a water D to H value greater than 6.6 times 10 to the minus 3. In plain words, that means the deuterium level in 3I/Atlas water was more than about 40 times higher than Earth's oceans and more than about 30 times higher than typical solar system comets. That was not a little off the chart, that was a different chart. And that is the moment the easy story breaks, because once the ratio climbed that high, the question stopped being, is this comet weird? The real question became, what process can push water that far away from what we thought was normal? A number that extreme demands a reason strong enough to make it. First, scientists had to ask whether the Sun itself could have done it. After all, 3I/Atlas had just swept through the inner solar system. Maybe solar heating cooked off one kind of ice faster than another and left the water ratio distorted. That sounds possible until you remember what isotopes are and how stubborn they can be. Heating can change how much gas comes off the surface at a given time, but it does not usually create a whole new deep isotopic history out of nowhere. The ratio between deuterium and hydrogen in water is mostly telling you about when the water formed, not about a quick warm-up during one pass near a star. So the Sun could expose the signature, but it was not likely to invent the signature. Then there was the question of damage during the long trip between stars. Could millions or even billions of years in interstellar space have altered only the outer layers and produced a false reading? Cosmic rays can change some material over huge spans of time, but that kind of processing is not the clean, strong, well-known path for making water this deuterium-rich across a whole active comet. That leaves the trail pointing backward, not forward. Backward to formation, backward to the cloud of gas and dust where this object first came together, backward to a region that was much colder, less blasted by radiation, and less warmed by later changes than the regions that shaped most of the water we compare it to. Here is the key chemical point. The reactions that enrich water with deuterium work best at temperatures below about 30 Kelvin. That is about minus 406 degrees Fahrenheit, or so cold that everyday language almost stops helping. In those deep freeze conditions, the chemistry starts favoring deuterium in a way warmer environments do not. But temperature is only part of it. The material also seems to have been less irradiated, which means it was exposed to less energetic light or particle damage. And it seems to have been less thermally processed, which means it was not repeatedly heated up and reset. Put those together, and you get a place where an extreme water signature can form and stay locked in. That is why the strongest explanation was not something happened on the trip. It was, this object was born in a far colder nursery than ours. Salazar Manzano said the conditions that led to our solar system are much different from how other planetary systems evolved in other parts of the galaxy. That is a careful sentence, but the meaning is huge. For years, many people talked as if our solar system might be a decent middle-of-the-road example. Not perfect, not unique, but common enough to use as a guide. 3I/Atlas pushes back on that comfort. It says the chemistry that shaped us may be only one style among many, and maybe not even the dominant one. Now remember what a comet really is. People call comets dirty snowballs, but that simple phrase hides something important. A comet is cold storage. It keeps old material, sometimes very old material, and if you read it correctly, you are reading preserved conditions from the time and place where it formed. That is why this water ratio hit so hard. It was not just a funny feature in a passing object, it was a direct chemical window into another planetary system. And because this was the first time scientists measured deuterated water in an interstellar object at all, the result instantly became a new benchmark. But one benchmark does not solve the whole case. A ratio can tell you the birthplace was extreme without giving you a street address. It can say far colder than here without saying exactly which star, which disk, or which zone inside that disk. So the next question was obvious. Could any other clues narrow the birthplace further? Pause here and make your next call before the trail sharpens. Was 3I/Atlas likely born around a young star, like a rough early copy of our own system, or around something much older and stranger? Write your guess now because the next clue changes the picture again. Another team used the European Southern Observatory's Very Large Telescope, or VLT, to study the comet in a different way. Their broader findings pointed to an origin in the outer regions around an old, low metallicity star. Low metallicity sounds technical, but it simply means the star had fewer heavy elements than stars like the Sun. That usually points to a star that formed when the universe was younger and less chemically rich. Why does that matter? Because a system built around an older, more chemically simple star, may not build comets in the same pattern our system did. The mix of raw ingredients changes. The temperature map changes. The way ice forms, survives, and moves through the system can change too. This does not mean scientists have found the exact home star of 3I/Atlas. They have not. But the picture is getting tighter. Instead of somewhere out there, the evidence starts pointing toward a very cold outer region in a system that may itself have been older and chemically different from ours. And that matters because the water ratio was never meant to stand alone. It fits with the larger story that 3I/Atlas is not just an ordinary comet ejected from an ordinary place. It looks like a messenger from a system shaped by conditions we do not usually sample. Each extra clue does not replace the water result. It strengthens the need to take it seriously. NASA's own summary of the comet added more context. By December 2025, Sphere-X observations showed infrared light from dust, water, organic molecules, and carbon dioxide in the comet's coma. That told scientists the object was chemically active and rich enough to study in more than one way. It also meant the water story was part of a bigger chemical scene, not a lonely signal floating by itself. The basic physical numbers help too. As of August 20th, 2025, estimates place the object somewhere between about 440 meters across and up to about 5.6 kilometers wide. Its closest pass to Earth was about 1.8 astronomical units, around 170 million miles. Its closest point to the Sun came around October 30th, 2025, at about 1.4 astronomical units, roughly 130 million miles. Those distances matter because 3I/Atlas never dove extremely close to the Sun like some sun-grazing comets do. It was warmed, yes, but not roasted to pieces in the deepest furnace of the inner solar system. That makes it harder to blame a short, violent solar bake for the extreme isotope signal. Again, the trail leans toward inheritance from birth, not a last-minute makeover. Now, here is a subtle point that often gets lost. When people hear, "unlike anything ever measured," they imagine a monster object doing everything in a crazy way. But the phrase is really about the water ratio itself. The reason it stands out so much is not that 3I/Atlas broke every rule in every category, but that one key chemical fingerprint went far beyond known limits. That makes the story more powerful, not less. Wild objects can be easy to dismiss as chaos. A focused chemical signal is harder to wave away. It tells you that one specific part of the object's history was shaped under very specific conditions, and those conditions were not like the ones that gave rise to our usual comet samples. Still, good investigations do not stop at the strongest explanation. They test the weaker ones until they fail. Could the result come from sampling bias, meaning we only saw the part of the comet most rich in deuterium? Could jets from one unusual patch have fooled us? Could the coma around the nucleus have mixed gases in a way that briefly exaggerated the ratio? Those ideas are not silly. Comets are messy. They rotate, vent gas unevenly, and throw out material from changing spots. But to turn an ordinary comet into something more than 30 times above the usual comet range would require a very large distortion. And the simplest path to that kind of signal is still a genuinely extreme source composition. Here is where I want your read before the next reveal. If you had to choose, would you blame a strange viewing angle and tricky outgassing? Or would you say the comet itself was built from truly different ice from the start? Put your answer in the comments before we lock down the verdict. The deeper scientists looked, the more the second answer kept winning. The paper's own conclusion was that the elevated deuterium enrichment points to water formed under colder, less irradiated conditions and from less thermally processed material. That wording matters. It is not saying maybe the sunlight fooled us. It is saying the water itself carries the mark of a different birth environment. Even the measurement method fits that conclusion better than critics might expect. Because ALMA detected HDO directly, the deuterium-rich part was not imaginary. What had to be modeled was the amount of ordinary water being released at the same time. That adds uncertainty, yes, but uncertainty is not the same as weakness, especially when the final ratio still lands far beyond anything we normally see. And remember, this was not random guesswork with no anchor. The team used methanol line excitation to infer the water production rate. That sounds technical, so here is the simple version. They used the way another molecule was behaving in the coma to estimate how much ordinary water had to be there, even though H2O itself was too faint for a direct ALMA detection. Scientists do this kind of indirect work all the time when direct measurement is hard. The real test is whether the indirect path is physically reasonable and whether the result fits the bigger chemical picture. In this case, it did. The ratio lined up with a birthplace story that also matched what we know about deuterium chemistry in extreme cold. So the case was getting stronger, but the mystery was not finished. Because if 3I/Atlas formed in such a cold, lightly processed region, then how common are such places? Is this object a rare freak from a rare system? Or have we simply been blind to a whole class of planetary birthplaces because interstellar visitors are so hard to catch? That is one reason this story feels bigger than one comet. We have only found 3 confirmed interstellar objects so far. That is a tiny sample, too small to tell us what normal looks like beyond our solar system. One strange object in a small sample could be luck, but it could also be our first honest hint that the galaxy is chemically more diverse than we let ourselves believe. There is another reason the story hits so deep. Water matters to us in a way almost no other molecule does. When astronomers talk about water ratios, they are not just measuring ice. They are measuring the history of one of the ingredients that shaped planets, oceans, and maybe life in places we have not yet seen. That is why the number keeps pulling people back. More than 40 times Earth's ocean value is not just a stat for specialists. It tells us the water that helped build our world is not the only kind of cosmic story water can tell. Some systems may store their water in colder, darker ways for much longer, and 3I/Atlas may be proof. Now the tone of the story changes. Up to this point, we have mostly followed what was discovered. From here on, the real tension is what remains unresolved. Because a strong verdict about the water ratio does not mean the whole origin story is settled, and the unsolved parts matter. We still do not know the exact star system that launched 3I/Atlas toward us. We do not know when it was ejected. We do not know whether it came from a calm outer belt, a violent scattering event with giant planets, or some other dynamical shove. And we do not yet know whether future interstellar comets will look anything like it. We also do not know how much the wider chemistry of 3I/Atlas will reshape our theories once more studies are folded in. Every new molecule added to the picture can tighten or loosen the current story. That is why scientists stay careful even when a result is dramatic. They know one strong clue is powerful, but a full map takes time. Even so, some explanations are already fading. The idea that the ratio is just a brief surface effect now looks weak. The idea that the trip through interstellar space created the signal also looks weak. The explanation that still stands after repeated pressure is the one tied to origin, deep cold and preserved material. Before we deliver the final verdict, take one last position. Was the strange water ratio mainly created by the journey through space, by the recent pass near the sun, or by the place where 3I/Atlas was born? Lock in your answer now, because this is where the case stops circling and starts closing. The real reason 3I/Atlas has a water ratio unlike anything ever measured is that its water was born in a far colder and less altered environment than the one that shaped the water in our own cosmic neighborhood. Not during the trip, not during the flyby, at birth. That is the cleanest answer supported by the data. The deuterium-rich water points to temperatures below about 30 Kelvin, to low irradiation, and to material that escaped the kind of heating that would erase or soften that signature. In other words, 3I/Atlas appears to have formed in a frozen outer region of another planetary system where the chemistry strongly favored deuterium and then preserved it. And the picture may be even sharper than that. The VLT-based work suggests the host system may have centered on an old, low metallicity star. If that part of the story holds up, then 3I/Atlas was not only colder than our formation environment, it may also come from a system shaped by an earlier and less chemically rich era of the galaxy. That does not overturn the verdict. It deepens it. The water ratio is extreme because the object likely formed under physical and chemical conditions that were different from ours in more than one way. Colder, darker, less processed, and maybe older at the system level too. So let us walk back to the opening claim. Yes, the number really does rise past 40 when compared with Earth's oceans. Yes, it also stands more than 30 times above typical solar system comet values. But the bigger truth hiding behind those numbers is not that 3I/Atlas is magically bizarre. It is that our old idea of what counts as normal may be too local. That is why the phrase, "unlike anything ever measured," matters so much here. This was the first direct measurement of deuterated water in an interstellar object. So the result did not merely extend a line on a chart. It opened a door to a kind of chemical comparison we had never been able to make before. And once that door opened, a hard possibility came with it. Maybe our solar system is not a safe template for the galaxy. Maybe water, the thing we use as a familiar anchor, can carry very different histories depending on where and when a system forms. Maybe what feels standard to us is only standard inside our small corner of space. That should matter even if you never plan to read a science paper, because this is really a story about where worlds get their ingredients. If water can arrive with such different chemical memories, then planets, moons, and maybe even places that could host life may start with more varied raw material than we imagined. The future search for other habitable worlds gets more interesting, not less. It also matters for something more human. We tend to look up and assume the universe is built from versions of what we already know. 3i/Atlas is a reminder that the universe keeps records we did not expect. A small dark visitor can cross our sky and quietly tell us that the path to making worlds is wider, colder, and stranger than our home story alone. And that may be the most powerful part of the whole case. This object never came here to explain itself. It just passed through, shed gas, reflected light, and kept moving. Yet from that brief visit, scientists pulled out a clue about frozen chemistry in another system, maybe another age of the galaxy, and maybe a style of planet formation we are only beginning to understand. So the verdict is not just that 3i/Atlas has strange water. The verdict is that its water preserves the mark of an alien birthplace, and that mark survived long enough to reach us. The real reason the ratio is so extreme is simple in one sense and enormous in another. It was made in a colder kind of cradle than the one that made us. Subscribe, turn on notifications, and stay with this investigation as new interstellar visitors and new measurements arrive. Then tell me in the comments which idea hits you harder, that 3i/Atlas came from a far colder world, or that our own solar system may be less typical than we thought. Share this with someone who loves space mysteries that get stranger the closer you look, and thank you so much for watching.